Okay, so this is section 8.8, last section of chapter 8. Topic is improper integrals. So improper integrals are integrals where the limits of integration are infinity, or the function approaches infinity. And so there's really two things that can happen. One is you can get a number, and the other one is it's an infinite answer. So the way you do this is that you rewrite the integral so that it actually has a finite limit, and then you take the limit as the upper limit goes to infinity. So let's look at this example. So this is the case of where the function, the x value, goes to infinity, and this is a plot of 1 over x squared. And we're looking for the area underneath the curve from x equals 1 to all the way to infinity. And you might think, well, if that goes into infinity, doesn't that mean I have an infinite area? And the answer is not necessarily. It depends upon how quickly this thing approaches 0. If it approaches slowly, then it's going to be an infinite answer. If it approaches more quickly, so the question is, what is slowly and what is more quickly? We'll find out that later. But it approaches a finite value. If it approaches a number, a real number, then of course it's a finite value. So that's what improper integrals are. So what we do is we take the original expression and we take the limit as b goes to infinity of the integral from 1 to b, and then you have your function. So that's the main thing here. And then you can see where we need to have limits, because that's part of this. That's why we had to do L'Hopital's rule. And for most cases, the limits will be easy to evaluate, but there are cases where you end up with indeterminate results, so you need to know how to handle that. But probably 75–80% of the stuff we'll do, we won't have to use L'Hopital's rule. And the whole idea here is that, this gives me a finite answer, the integral. So we're integrating to a finite answer, but then we're letting the limit approach of b approach infinity. So we're doing the limit of the result of the integration, not using infinity as an upper limit, because infinity does not exist. So we can't make it equal to infinity, but we can take the limit as b goes to infinity to get the answer. So it's kind of a technical point. I mean, you could actually just leave this off and put infinity in at the end, and it would still be the same. You'd probably get the same answer. You would get the same answer. It's just a little technicality, but I want you to make sure you do it this way. Okay, so once you've changed the limit from infinity to b, then you just do the integration, and so this will be x to the minus 2 power. If we rewrite that as move that to the numerator, so you have the integral from 1 to b of x to the minus 2 power dx. So now it's in a form that we can use the power rule. So what we do is we add 1 to the exponent, and we divide by the new exponent, and then we evaluate it between the limits as shown in the previous step. So remember, once you've completed the integration, you've applied the integration rule, you don't have the integration sign anymore. And because I have limits, I don't add the arbitrary constant c. So before I actually plug in the limits, let's rewrite it as negative 1 over x, evaluated between 1 and b. So what I've done is the negative sign, the denominator becomes x to the first power, which is x. Okay, now we plug in the limits of integration. So the answer is negative 1 over b minus, or plus, well actually minus a minus, so let's put it in there. So you're subtracting the lower limit. You're evaluating the function at the lower limit. And here, again, negative times negative, so this becomes positive 1. So I get negative 1 over b plus 1. So if I plug in infinity, I'll get 1 over infinity. So this term goes to 0. So I'll get 0, and this doesn't change at all because it's not involving b, so the answer is 1. So if I go back to my curve, the area underneath this curve is a finite number, and it's actually 1, which is kind of interesting. 1 would be this much area, square 1 square unit. And if you add all those little bits up, it's going to exactly equal 1 also. So that's what we just did. So it says some improper integrals converge. That's what just happened. Whereas some improper integrals diverge. Also, some improper integrals involve going to infinity on the x-axis, and some involve going to infinity on the y-axis. So the one we just did was infinity on the x-axis. So we had it converge to an answer 1, and we had that. So we're going to have to look at some of the other cases. So let's look at this, which is, we had 1 over x squared, so this is 1 over the square root of x. So if I plot that, looks like that. And I'm looking for the integral between 0 and 1. So this is actually well, let's come back to that one. Let's do the other. So what if we go from 1 to infinity? So this is like the last one, except 1 over the square root of x, which is x to the 1/2 power. So then I can move that to the numerator, so I get x to the minus 1/2 power dx. So what is that area? That's this area right here. So if you compare this with 1 over x squared, you'll notice that this approaches the x-axis more quickly. This one approaches the x-axis more slowly. So at least this should at least be bigger, but it may be approaching so slowly that it won't converge. That's what we'll end up finding out. So again, what you do is you change this to a finite limit b. So we say take the limit as b goes to infinity of the integral from 1 to b of x to the minus 1/2 power dx. Okay, so now we integrate. So the integral, you add 1 to the exponent, divide by the new exponent, evaluate it between 1 and our letter b. Okay, so then we plug them in to the equation. Notice this divide by 1/2 is like multiplying by 2, so I'm just going to do that. And let's put an intermediate step here, so I'm not just leaving stuff out. So what you'll get is 2 times the square root of x, evaluated between 1 and b. So the 2 comes out, and so I have the square root of b minus the square root of 1. And then if I take the limit as b goes to infinity, well, the square root of infinity is still infinity. So the result of this is infinity. So we can say that the original integral is unbounded. Means it keeps getting larger and larger and larger. So it goes to infinity. So it's unbounded. The value of x is going to infinity. So when this was 2, it was bounded. when it was 1/2, it was unbounded. So there's some point where it goes from being bounded to unbounded for this value, this coefficient. It turns out that between 0, in terms of if you have 1 over x to the p power, say, if p is between 0 and equal to 1, it's unbounded. So in this case, we have a half, which is this case. If you have p greater than 1, then it's bounded. So our first case was p equals 2, and it was bounded. But p equals 1 is where, if p equals 1, it doesn't work. If p equals 1.000001, it's going to work. P 0.99999 is going to not work. Okay, so let's look at the other case. This is the same function here, except we're approaching the y-axis. So we're integrating from 0 plus, basically, to 1. So this is not an infinite limit, but the function approaches infinity. Well, actually, it's 0. So we're going to replace 0 with b in this case. So you don't replace b with infinity with b. You replace the limit where the function goes to infinity, which is, in this case, the lower limit. And notice here, going this way, it approaches the x-axis slowly, but with respect to y, it approaches it much more quickly. So you might expect that this is going to converge, and this one doesn't converge, which if you did that, you'd be correct. Okay, so what we're going to do is we're going to replace 0 with b and keep 1 the same. This would be x to the minus 1/2 power dx. And you take the limit as b doesn't go to infinity. In this case, b goes to 0. So we still have our limit because we haven't evaluated the integral yet. So the integral of x to the negative 1/2, you add 1 to the exponent, divide by the new exponent. You evaluate it between b and 1. So we can take the 2 outside. The limit as b goes to 0. And what we have is the lower limit. Well, this is a square root, so I'm going to change it to square root. So you're going to get square root of 1 minus the square root of the lower limit, which is b. Then you let the b go to 0. So you're going to have 2. Well, the first term is unaffected by this limit, so it's just going to be 1 minus, when b goes to 0, you get the square root of 0, which is 0. So the answer is 2. So it's kind of interesting. This is 2. When we went the other way with 1 over x squared, it actually went to 1. That makes me, did I make a mistake over here? Let's go back. No, because we were this was x squared. Yeah, so we ended up, didn't get an extra thing in there. So that's correct. So that's pretty much it. Like I said, that we have this middle point, which we haven't looked at. So this is a case where, again, you've got 1 over x, which looks something like this. And we're going from x equals 2 to infinity. Not x equals 1, but you know, all the differences. You've got this little bit on the front here. So if it's unbounded, it's not going to be due to this one little extra bit. That's the case. So what we do is we say the limit as b goes to infinity, integral from 2 to b, and I'm going to rewrite 1 over x as x to the minus 1 power. Okay, write our limit down. We're going to do the integration, so you get x. Actually, I didn't want to do that. That's the one case we don't use the power rule. So what we get is the integral of 1 over x dx is the natural log of the absolute value of x. And we're going to evaluate that between 2 and b. So you get the limit as b goes to infinity of the natural log of the absolute value of b minus the natural log of 2. And then you let b go to infinity. So you'll have the natural log of infinity, which is infinity. So you get infinity minus the natural log of 2, which is still infinity. So in this case, this is unbounded because this limit goes to infinity. Now here's kind of the opposite. We did 1 over the square root of x. Here we've got integer or a exponent greater than 1. And if you draw that, you'll notice that in this direction it approaches the y-axis more slowly, approaches the x-axis quickly, which we proved this converged, but turns out this one will diverge. But let's just go through the process to show that it does. So we're going to take the limit as b approaches the value where the function goes to infinity, which is 0. So I integrate from b to 3. X squared, 1 over x squared is x to the minus 2 power. So when you integrate that, you get x to the minus 1 power divided by negative 1, evaluated between b and 3. So this is negative 1 over x between b and 3. Now, we evaluate the function at the limits. We don't do the limit yet. These are the limits. This is the limit. So we get negative 1 over 3 minus negative 1 over b. And the limit is going to 0, not to infinity. So the first term is unchanged, so you get negative 1/3. But the second term is 1 over 0. 1 over 0 is infinity. So this is infinity. So we'd say this is unbounded. So what converges going to the x-axis diverges going to the y-axis, and the opposite is true. Okay, now let's look at this one. This is one where we have to use L'Hopital's rule ultimately. So we have the integral from 0 to infinity of x times e to the minus x over 2 dx. And we would rewrite that as the limit as b goes to infinity of the integral from 0 to b of x e to the minus x over 2 dx. And I have sketched the curve, or the computer sketched the curve, and you can see what it looks like. You know, one of the requirements for an improper integral to have a possibility of being a finite value is for the function to approach 0 as x goes to infinity. We'll see that again in the next section when we talk about series. But right now we're just talking about functions. So it's hard to tell. I mean, just looking at it, is it approaching fast enough or not? I don't really know. So that's why we have to do the problem in this case. So how do you solve this thing? Also, just to let you know, e to the minus infinity is 0. E to the 0 is 1, and e to the infinity is infinity. And that's because, you know, if we plot e to the x, it looks like that. So that's e to the negative infinity approaches 0. E to the 0 is 1, and then this thing goes unbounded in the y direction. Okay, so there it is. So you have to use integration by parts on this because we have x times, we have a product of some kind. We have a simpler part and a more complex part. So before we use integration by parts, so we're gonna initially, we always want to initially rewrite it in terms of the limit. So we're going to take the limit as b goes to infinity of the integral from 0 to b of x times e to the minus x over 2 dx. And we will use integration by parts. So u is the part whose derivative is simpler than the original function, and dv is the rest of it, e to the minus x over 2 dx, that we can, the more complicated part that we can integrate. So integrate that, and remember when you integrate and you have just x times some constant, you divide by the constant. So what we're doing is we'd have 1 divided by negative 1/2. So this is negative 1/2 x. So we're going to divide by negative 1/2 x. So we took the derivative, we multiply by negative 1/2 x. And then the integral of e to the u is e to the u. So it just becomes e to the minus x over 2. Or if we take the reciprocal, you get negative 2 e to the minus x over 2. So then what we have is the integration by parts equation. U dv is equal to u times v minus the integral of v du. So what we'll have is, we'll have the limit as b goes to infinity. And remember what we do is, for this part, when you have a definite integral, you plug them in and then you put the limits. So u is x, v is negative 2e to the minus x over 2, evaluated between 0 and b. So that's the first part. And then the second part, and I'll just do the limit thing here separately. So then you do the limit of that part. So you have the integral from 0 to b, and v is negative 2 e to the minus x over 2 times dx, which is du, which is dx. So then what we do is we're going to integrate the second thing. So we got this first part. Let me factor out the negative 2. So it's negative 2x e to the minus x over 2, evaluated between 0 and b. And then the second one, you get a positive sign, negative times negative. You get your constant 2, and then you integrate e to the minus x over 2, which we've already done. That was 2 e to the, actually negative 2. So it's negative 2 e to the minus x over 2. And now since I've integrated, now I can put on the limits again. So let's recap. Negative times the negative is positive. The 2 comes out. The integral of e to the minus x over 2 is e to the minus x over 2 divided by negative 1/2, which is negative 2. And I need to put the limit in there. Didn't do that. Plus the limit as b goes to infinity. And finally, we'll plug in the limits. So we get the limit as b goes to infinity of negative 2. And so we have x. So the upper limit is going to be b e to the minus b divided by 2. And at the lower limit, it's going to be 0 times e to the minus 0 over 2. That term is going to go to 0. 0 times anything is 0, except maybe 0 times infinity. And then you have the second part, which, let's factor out the negative 2 times negative 2, so it's going to be negative 4. we get negative 4. And we're going to evaluate e to the minus x over 2 at those limits. So we get e to the negative b over 2 minus e to the 0 over 2. Now the last two terms are easy because e to the 0 is 1. So you'll have negative 1 times negative 4. So it'll give you 4. This one goes to 0 when you take the limit, which again I forgot to write down. I keep forgetting that. So it's negative the limit as b goes to infinity. Some equal signs up. Okay, so actually don't need equal sign there because that's part of the whole thing. Okay, so that the first one is this goes to 0. I'm going to take the negative 2 outside of the limit. So it's going to be the limit as b goes to infinity of b times e to the minus b over 2. Here, if I apply the limit, I'll get b to the minus infinity. Well, b to the minus infinity is 0. So this one's going to go to 0. And then I have a minus times a minus, which is a plus. So I'm at plus 4 times e to the 0, which of course is 4. E to the 0 is 1, so that's going to be 4. The only thing we have left is this part, and this is the one we have to use L'Hopital's rule because we're going to have infinity times e to the minus infinity, which is indeterminate. So we need to, let's just evaluate this limit here by itself, and then we can plug it in. So if you have to take the limit as b goes to infinity of b times e to the minus b over 2, it's not a quotient, so what we're going to do is we're going to make it a quotient. So you'll have b over e to the positive b over 2. So when this goes to the denominator, make it positive. It's still indeterminate. Now it's infinity over infinity. So what we do is we take the derivative of each part with respect to b. So you get 1 divided by 1/2 e to the b over 2. So that's using the chain rule. So the derivative of b over 2 is 1/2 with respect to b. So you get 1/2. That's where the half comes from. The derivative of e to the u is e to the u. And now you can see if I take the limit as b goes to infinity, you get 1 over infinity, which is 0. So this part here is negative 2 times 0, it's 0. So the final answer is just the one term remains, which is the last term. And so you get 4. So that's the area underneath this curve from here to there. And you kind of think, think about it. This is about 2/3. It's about 2/3. This is about a little over a half. If you look at the square as being 1 by 1. Let's actually just kind of estimate how much those are. So let's move those to a new thing, and then we'll just stretch it out so we can kind of estimate things. I'm going to estimate what I think the areas under those things are. Well, if this were, let's see right there, that'd be a half. So I'm going to say 0.4. This would be a half. So this, I'm going to say this is 0.6. I'm going to say that's 0.6. And this one is probably 0.55. That one is probably 0.45. This one is probably 0.35. That one's probably 0.25. That's maybe 0.2, and then they get smaller, smaller, smaller. So if I add all of those things up, so let's add them up as hundreds or as two-digit numbers. So you'll get 40, 100, 160, 160, 100 and 215, 260, 295, 320, 340. So I'm approximating that's about 3.4. And then you got out to infinity, gives you another 0.6. Okay, what else have I got to do here? Left to do. Yeah, this is one of those cases of, am I approaching the x-axis fast enough? And if you plot this 1 over the cube root of x, and you plot it, you can see it how it approaches the x-axis more quickly, where it doesn't approach the y-axis. So what you would, just from observation, you'd say this is bounded, but this one is unbounded. Like this one would be unbounded because its exponent is less than 1. So if there's no point in going through it if we can recognize it immediately. There's a rule about x to the n or x to the p. If p is less than between 0 and 1, then it diverges if you go to infinity. If you go to a vertical asymptote, then it will diverge. So this one converges, this one diverges. So I'm not even going to do that one. We could do this one. That would actually give us a number. So maybe it's worth doing that one. Again, we're going from the plus side because we're going to take the limit. Okay, so this is x to the minus 1/3 power dx, this one right here. So you change it to the limit as b goes to 0, which is where the function goes to infinity, of the integral from b to 1 of x to the minus 1/3 dx. Okay, so you add one of the exponents, x to the 2/3, divide by the new exponent, 2/3, evaluate between b and 1. So 2/3 divided by 2/3 is multiplying by 3/2, so we'll have 3/2, and we'll have x to the, to the 2/3. So we'll plug in the upper limit, so you get 1 to the 2/3 minus 0 to the 2/3. Actually, b to the 2/3. And we take the limit as b goes to 0. And so then we take the limit, and the first part we just get 3/2. And in the second part you get 0 to the 2/3. Well, 0 to the 2/3 is 0, so the answer is 3/2, so it is bounded. And here's the rule. 1 over x to the n dx. If n is from 0 to 1, it diverges. If n is greater than 1, it converges. And the opposite is true this way. If you integrate to a asymptote, it converges. When you go from 0 to 1, it diverges if it's greater than 1. So that's the rule. I'm also going to... okay, we've got 2 more problems to go through here. And so this is one of these where the function goes to infinity at x equals 2. Because what you'll have is 2 squared, which is 4. 4 minus 4 is 0. So you get 0. And the function does not actually exist between positive 2 and negative 2 because you get a negative square root at those points. So this is the limit that we're going to replace with b. So we'll rewrite that as the limit as b goes to 2 of the integral from b to 4. Okay, so let's okay, so now the question is, what's the integral of this? And if you look in your book and you look under the different integrals, you would see, so I'm pulling out my list here, and you go to the bottom of the first page, you'll see formula 18. Formula 18 says that the integral of du over u times the square root of u squared minus a squared is equal to 1 over a times the arc secant of the absolute value of u over a plus c. So in our case, here, u is x and a is 2, because we have x squared minus 4 squared, u squared minus a squared, and x is u. So that works out perfectly. So what we do is we'll take the integral, and what we get is we have the constant 2, and then we'll have 1 over x, square root of x squared minus 4. So it'll be 2, 1 over a, well a is also 2, times the arc secant of the absolute value of x divided by 2. And so this was an indefinite integral, but we're doing a definite integral here. So we're going to go from b to 4. These two will cancel out. So the next step is we're going to evaluate the function at the upper limit. So you have the arc secant of the absolute value of 4 divided by 2 minus the arc secant of the absolute value of b divided by 2. And so we'll get the arc secant of 2. So what is the arc secant of 2? Well, the arc secant of 2 is equal to the arc cosine of a half. So we take the reciprocal of that number and change it to cosine. And we could plug that in our calculator, but let's just do the unit circle thing here to figure out what it is. So cosine is the x coordinate on the unit circle. And so if we mark a half, so we're halfway between here and here, and we draw it up like that, you're going to have the angle is going to be up there. So remember you have pi over 6, pi over 4, pi over 3. So the angle whose cosine is a half is equal to pi over 3. So that's pi over 3, and that's not going to be affected by taking the limit. Now the second question is, what is the arc secant of 2? So what we're going to do is let b equal 2, and so that's the arc secant of 1, which is the arc cosine of 1 over 1, which is 1, and the angle whose cosine is 1 is 0. 0 radians. So this term is going to go to 0 when you take the limit. So all we're left with is the arc secant of 2, which is pi over 3. So the answer, the integral of this whole thing, is pi over 3. So the area underneath this curve is going to be pi over 3, which is about 1 unit, because pi is 3.14, so pi divided by 3 is going to be about approximately 1. And you can kind of, that's 1 unit, and you can kind of imagine that this part, and you stuff this little part in there, and then this little part, it's going to fill up that extra bit. So it looks like it's the right answer, just from an approximation standpoint. And then the final one we're going to do is this one, which is kind of like the one we did earlier, except we're integrating from 1 to infinity, and instead of from 0 to infinity, and we have an exponent of negative 2x. The other one was, I think, negative a half x. So again, this is a case where you have the limit is infinity. So you're going to take the limit as b goes to infinity of the integral from 1 to b of x times e to the minus 2x dx. Now we're going to have to use integration by parts to solve this integral. So u is going to be x, and dv is going to be equal to negative, not negative, it's going to be e to the negative 2x dx. So the derivative of u, du is dx, v. So again, we are integrating, and the u substitution means that we're going to end up dividing by this coefficient. So we're going to have a negative 1/2 from this integration, and then the trig function, not the trig function, but the exponential function will stay the same. It'll still be e to the minus 2x. You get this negative 1/2 from dividing by negative 2. So integration by parts says that the integral of u dv equals u times v minus the integral of v du. So we're just doing the indefinite integral, and then well, actually, let's put the definite stuff in there. So remember, what we did is you take u times v, and then you evaluate that from 1 to b. And what I'm going to do is take the limit as b goes to infinity, and then we'll put this whole thing in the brackets, because we're going to have to do that. And then the second part is negative the integral of v, which is negative 1/2 e to the negative 2x. So that's v times du, which is dx. We're integrating from 1 to b. Put the other bracket to put that all together. So everything seems to be matching up. Okay, so the next thing we'll do is we'll integrate the second part. First part, we're just going to clean up a little bit. Negative 1/2 x e to the minus 2x evaluated between these two limits. The negatives will cancel out, so you'll have plus 1/2 times the integral of this, which we already did over here, which is negative 1/2 e to the minus 2x. And then now we're going to put the limits, because we've integrated it. And by using integration by parts, we went from x times e to the x to just e to the x type format. And then we do a right bracket. Okay, so now we're going to plug in the limits to each part. So we'll get negative 1/2 times b. So for x, we're going to plug in the upper limit, b, e to the minus 2b. And then we're going to subtract this. So we'll have a negative times a negative. So let's make that positive. This will be negative. This is positive. You get 1/2 times 1 times e to the minus 2 times 1. So that's that one done. And then you have the second part, which is plus 1/2. Well, you get 1/2 times negative 1/2, so it becomes negative 1/4. So you'll have negative 1/4 times e to the minus 2x, but evaluated at b, and then subtract evaluating it at 1. So that becomes negative 2 times 1. Close this parenthesis to match that one, and then use the bracket. So some of these are going to go to 0, because as b goes to infinity, well, this one we're going to have to use L'Hopital's rule, so we're going to have to come back to that one. This one is going to go to 0, because you get e to the minus infinity, which is 0. This is going to be 1/2 e to the negative 2 power. This will be minus 1/4, or plus 1/4, because you have negative times negative. So the second part, we're going to have 3/4 e to the negative 2 power. But let's do the first part. So what we're looking at is the limit as b goes to infinity of, let's factor out the negative 1/2. So we're just looking at b times e to the minus 2b. So if we plugged b in, we get infinity times 0, because e to the minus infinity is 0. So you get an indeterminate form. But we can't use L'Hopital's rule, so we have to rewrite it just like we did before, where you take b divided by e to the positive 2b. Now you'd get infinity over infinity, which is still indeterminate. So we have to take the derivative. So if you take the derivative of the numerator and the denominator, you'll get 1. We're taking the derivative with respect to b. We get 2e to the 2b. And now you can take the limit, because it won't be indeterminate, because the numerator will be 1 and the denominator will be infinity, because you have e to the infinite power. So this just becomes negative 1/2 times 0. This limit becomes 0. So that term goes to 0. And then all we're left with is 1/2 plus 1/4. So we get 3/4 times e to the minus 2 power, or 3 divided by 4e squared. And I guess we wanted to come out with the decimal value. I'm not sure what the book is expecting, so I'm trying to find my calculator. There it is. But I'm going to look in the answers here anyway, just to confirm the last two problems that I did, which I don't know if I put the numbers on there or not. So I'll have to look it up in the book. So I'm just going to pause this for a second. Okay, so that one was correct. And the next one is, let's see which problem it is. Number 9. No, it's not 19. Okay, I'm pausing again because I can't find it immediately. So I couldn't find the problem in the book, but I went online and just did an online definite integral calculator, and I ran with an upper limit of 1,000 or something. So I knew that would give me the approximate. I couldn't put in the infinity, so you get that, which is the same as that. So if you take 3 divided by 4e squared, you'll get 0.1015. So that one was done correctly too. And there are the second bunch of problems for, or actually I'm not sure if I had a first bunch or not. I'm thinking about partial fractions. Anyway, those are the problems for number 8. So those will be due Friday after break. And then we said we're going to have the test on Chapter 8 Tuesday after, not after break, but the week after